Hello all of you. Welcome to the fifth lecture in the course on analysis and modeling in chemical engineering. In the last lecture, we have continued the discussion on the spring and dashpot model, and combining the previous and the earlier lecture. Basically, we have done three kinds of model for that problem. A fundamental model that is based on the accepted theory, Newton's second law, an empirical model that came from data fitting, and there is a modeling by analogy, that is by comparing the system with an RLC circuit. And then I also discussed a modeling recipe to follow, or the steps of the model development to follow in order to come up with a good model that gives you a reliable prediction of the experimental behavior, right? So I want to begin with that recipe now and take some examples. But before I jump into chemical engineering, I want to begin with some daily life examples that you can easily relate to, so that you understand the basic flow of the development of a model, what really goes into a model development process. And what I want to basically convince you is that once you have that kind of an algorithm in mind, chemical engineering problems are no different. So without adding the lingo of chemical engineering, I want to do some simple problems that are more relatable, so that you get an appreciation of like what really goes into development of a model, right? So the example I want to take is the following. So all of you have seen this problem and all of you know about this problem, particularly those living in metro cities. The question is to develop a model to determine the time taken by a car to travel between point A to point B on a busy city road, right? Let us say you want to go from your home to school, or from here to, let us say, for a movie and things like that. So you always have to estimate a time, and typically nowadays mobile phones have a GPS enabled system that tells you it will take you 30 minutes or 40 minutes depending on the traffic. So therefore, there has to be a model that goes inside there that predicts how much time it is going to take. So we want to develop a model, something of a similar nature. Of course, not the exact algorithm that is being used by Google, I am not aware of that, but just to demonstrate the steps of model development and identifying the model parameters and things like that, right? So whenever I give you a problem like this, the very first response you may be having is that this problem is way too complicated, because on a busy city you have traffic, you have signals, there is traffic of all kinds, there is bicycles going on, there are bullock carts going on, there are traffic jams and things of that sort, and it looks fairly impossible to develop a model of this, right? So this is one common mistake that we always begin doing whenever we are posed a mathematical problem or a modeling problem, right? Like, what will happen if this is going on, what will happen if that is going on, right? Maybe you are hungry, but more than that, what if there is traffic, what if, I mean, like, earth is not completely flat, earth has a curvature, and I should go back and read about roads. This is a transportation problem, so I should pick up books on transportation and things like that. Are the aliens doing something? Are there some wrong math, this, that, and so on? So one start imagining like all sorts of possibilities that may happen in this problem, right? So the very first step in order to attack these kind of problem is to stop overthinking, right? And then to begin with, what I say, a simple model, and take baby steps that will always make your job easier, right? So what I suggest you in these kind of problems, not maybe for all the problems, but in these kind of problems where you think it is overly complicated, is to take baby steps. Start with simplest possibility. Let us say a car is going and there is no other car in the universe, this road is entirely empty, and then how much time will it take? There is no traffic signals whatsoever. Then let us say we add certain complications. Okay, speed is not constant. Okay, there is traffic. Okay, there is all kinds of traffic, right? So making models in a hierarchical fashion, that means first make a model that is very, very simple, then add certain complexities, then add some more complexities, and in the process of doing that, figure out what complexities must be introduced in order to get what I called optimum sloppiness, right? Of course, a tornado may happen. Of course, aliens may attack, but the possibility of that happening is very, 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 very less when I am going from here to, let's say, my home, or you're going from here to your school and things like that, right? So the key is to take the complexities which are, I would say, inevitable, that is always going to happen or most likely to happen, and do not worry about too many complications that may or may not happen, or they probably will not have that much effect on the problem, right? So we will do the same kind of, I would say, steps for this particular problem, beginning with a very simplistic model, and then we try to include more and more details, and the hope is that by the end of it we may have a model with the optimum sloppiness, right? If I begin with the sloppiest possible model, right? So before I even do that, let me go back and define it as a process, right? A process has an input and an output, and this is how I have been doing the problems in this course. Even a spring dashpot had an input and an output. The input in that case were the external force, output was the displacement. In this case, what is the input? We have to go from point A to point B. There are going to be geographical locations of those points. In principle, it is a vector, but let me, for the sake of argument, saying they are some scalar quantities xa and xb. Of course, we can complicate it further, but let's assume that it is just one dimensional and there are two positions xa and xb. That becomes now the scalar quantities, right? And the output clearly is the time it takes to go from here to there, right? And now I will introduce the model parameters. In the sloppiest model, I will have very few model parameters, as little as possible. Then as soon as I add more and more complications, the assumptions are going to go down and the model parameters are going to increase as I introduce more and more complications, right? So therefore, there are going to be disturbance variables which I am not considering in the model, and for the sloppiest model, you will have plenty of disturbance variables which can affect your results because you have not considered them. And as we do more and more complicated model, as we begin to relax the assumptions, we are going to have lesser number of disturbance variables, right? So we have to first think of what are the model parameters we must introduce, and then start from there, and then what are the model parameters I should now introduce, that is second important parameter, and then maybe third important parameter, and this way we will iteratively or sequentially, hierarchically, we will make more and more complicated models that will be more close to the reality. Okay. So let us begin with this simplest model. Let me call it model version 0.1, right? So we have a car that is going on a road, and I am assuming no traffic, and I am assuming that the car is moving with a constant velocity v, right? Now you can imagine that the distance between point A and point B is going to be some function of the geographical locations A and B and the route which I am taking, and there can be multiple routes. So you can imagine that I am considering only one particular route or route, and we are looking at the distance along that route, right? So we'll assume no traffic and we assume constant velocity v. Although it is the simplest possible model, at least we have accounted for the most important variables in the problem, which is the distance, that is a model parameter, or I would say in this case input parameter. because once I get xa and xb, I can derive the expression of the distance for a given route. So, xa, xb, s, these becomes my input variables, and then the distance becomes a function of that. So, basically it also in a sense becomes a input variable. It is a direct function of the xa, xb and the route taken, right. But the velocity of the car or the speed of the car, if I am talking about one dimensional traffic, that is clearly a model parameter, and we must have to account for that, right. So, if that is happening, then the time taken is going to be distance by velocity or the speed, right. Although I have taken this very simplest model, we can always imagine an extreme situations where this can still be valid. Let us say I am going on a road that is less traveled, nobody goes on that road, or let us say I am going like 3 a.m. in the morning when nobody is on the road, right. So, in those cases I can freely move at maybe a constant speed, and then I would like get there more or less in the same time. I mean, if I am going at 3 a.m. in the night, and if I know, let us say I have to go 100 kilometers, and my typical velocity of driving on a free road is, let us say, 100 kilometers per hour, then I can get there in 1 hour, and that model will not be wrong, because if the road is free, there is no traffic, this is the amount of time it will take, maybe 5 minutes here and there. But if you know your speed in the free traffic, you are not going to make an error, right. So, even though we are doing a simplest possible model, it has these basic ingredients. It captures the most important variable, that is the speed or the velocity of the car, the distance, that is input parameter as a function of the locations and route, and the time taken is distance by velocity. This is coming from basic physics, right. So, it already has the basic ingredients that we need in this model, right. Now, I want to take one step further and now really start thinking what is wrong in my model, right. Clearly, there are many things wrong, but what is the most wrong things in our model, right. So, in this case, I am assuming that the car is moving with a constant speed between point A to point B, right. So, typically speaking, let us say I start from A. So, in the beginning, my car will have 0 velocity. I will accelerate the car, go to a certain velocity, that is my maximum speed on a free road, and then I will drive until very close to point B, and then again I will kind of put a brake or slow down the car until it comes to a complete halt. And therefore, if I really think about my velocity versus time, it will never be like constant like this. It may be something like going up, constant, and then going down, right. So, the fact that the velocity is not actually constant is definitely a flaw, right. What I am trying to imagine, if I am doing this model strictly, is that the car was already going with a constant speed, probably self driven, and I jump in the car when it was already going with a certain speed, and I jump out of the car when the destination reached. That is not the reality. In reality, you will have an acceleration and deceleration, right. It is not that you are jumping into a moving vehicle and jumping out of the moving vehicle, right. That is clearly a problem, right. Then there is problem of traffic, and I want to include that, right. So, let us try to make another model. I will call it the model version 0.2. And what I want to do here is to incorporate the effect of traffic in the following way. So, we define a traffic density as the distance on the road that is occupied by the vehicles, right. And in general, you can have all kinds of vehicles, all kinds of cars, for example, hatchback, sedan, SUVs, but you can also have buses and trucks and things like that, right. So, this is one possible dimensionless traffic density that we can define. So, let us say we have some p different kinds of vehicle on the road, and let us say I equal to 1 refer to hatchback. So, they have a length L1, and we have N1 vehicles which are hatchback. Similarly, let us say L2 refers to the sedans, and we have N2 such sedans, and similarly we have N3 such SUVs, and similarly L4 buses and things like that. Right? So the numerator here, it represents the total distance on the road that is covered by the vehicles, right, or total part of the road that is covered by the vehicle. In this case, it is this distance plus this distance plus this distance, right. So as eta increases, we have more and more coverage of the road by the vehicles. In the extreme case, when eta is equal to 1, the entire road is covered by the cars. That pretty much means a condition of traffic jam, in fact the worst possible jam, because every vehicle is touching each other, right. So eta is equal to 1 is the maximum possible thing that can go to, and a smaller value of eta naturally means free traffic. When eta is close to 0, we are in a condition of free traffic that we had earlier, right. So now I can think of the velocity of the car or the speed of the car as some function of this eta, the traffic density. And if I know this function, I don't yet know how will I find this function, but if I know this function, then I can define the time as distance that I have to travel, that of course depends on the route, divided by the average velocity of the car, that depends on the traffic density. Okay. So the next step, we will try to use our intuition to think of how that average velocity should depend on this traffic density parameter, right. Now one thing is very clear, that if I am going from up to down on here, the eta is increasing, and as eta is increasing, the average velocity must go down, right. But how does it go down? Does it go down linearly as number 1 here, or does it go down like 2, where the initial slope of decrease is smaller but the slope is much higher later, or something like 3, where you have a higher slope to begin with and lower slope towards higher eta, or something like 4, where you have, let's say, a constant velocity until a while, and then it kind of goes down slowly linearly to 0, right. I claim, of course all of these are possible and there may be other possibilities. I claim that 4 is probably a more realistic situation. The reason being the following: let us say I take an extreme that we have one car in 1 kilometer distance. So clearly the car can move freely because the next car is 1 kilometer ahead on an average, right. Let us say now traffic density increases and we have 2 cars in 1 kilometer distance. The average distance now is 500 meter. So there is no need for this car to slow down because the other car is 500 meters away. Now let us say we have 5 cars in 500 meter. Now still the next car is 200 meters away on an average. Again, there is no particular need to slow down. But once we keep on increasing eta, you will start having a situation where the next car is, let's say, 10 meters away or 5 meters away. And now there is a reason to slow down the car, right. So the assumption here is, in the beginning, if I increase eta, it doesn't change the velocity very far from that maximum velocity of the car or the speed limit on the road, if one is following traffic, and one should follow traffic, right, traffic limits, right. So if one is following that traffic limit or speed limit, in that case the lower that speed limit is, the lower is going to be my Vmax, or if it is determined by the maximum speed the car can take. And beyond a certain point, there is going to be a decrease in the velocity, that it is going to reduce to 0. One can argue it is not a linear function, maybe a nonlinear function, but 4 is still a good, I would say, a qualitative estimate of how the behavior should look like. And now, beginning from nothing, I now have a model that is somewhat realistic, because now I incorporate for traffic. I know the maximum speed limit, I know the maximum speed the car can take. Based on that, I can decide on what is the speed in this area, and if I have some understanding of what the threshold is going to be, for a very careful driver it may be 20 meters, the next vehicle is there. For, I would say, a more trained driver, it can be like 5 meter the next vehicle is there. That may vary a bit, but not by a great margin, right? So one can kind of estimate how the profile of the velocity average is going to look like with increase in eta, right? And therefore, one can estimate the time now incorporating the effect of traffic. Now, clearly, the traffic is not going to be constant in the with the day, and we can in fact account for that as well in what I call the model version 0.3. And what I do here is I consider the fact that in the early morning you will have typically less traffic, and then in the rush hour, when there is a time to go to the office, the traffic will peak. In the afternoons, the traffic may go down, but not as low as in the early morning. And then again, when there is a time for office closure, again we will have a rush hour, the traffic will go up, and eventually again it is going to go down, and we will have a condition like the early morning condition, right? And from historical data, one can have, I would say, a function that dictates how the traffic density is changing with time. So now we have accounted for traffic density, and now we have also accounted for the fact that the traffic density can change with time of the day. We can do few more things in order to improve our model further. For example, if you have multiple routes, we can do this for all the possible route which are having different traffic and determine which one gives you the shortest time, and now it becomes an optimization problem, and that's what Google Map is typically doing. If some particular route has a more traffic, then it suggests you to take another route that may be more distance, but since the traffic is less, so therefore you may reach there in lesser time and things like that. So those kind of things can be implemented by the same kind of an idea. I need to know the traffic on each of those routes, and we can figure out the time taken on each route, and then figure out which one gives you the lowest possible time, right? Then one can also account for the traffic signals, for example. So let us say you have certain number of signals on the road, then you typically know how much waiting time you have on the signal. The signal may turn on for 30 seconds, 1 minute, 2 minutes. You can add those waiting times in the calculation. Let us say there are 10 signals, each having a waiting time of 1 minute, then you add 10 minutes, right, in there, and then you have, I would say, a more improved model that is, of course, more complicated, but more realistic and things like that. And finally, one can also account for, particularly in Indian context, the heterogeneity in the traffic, right? So you don't only have cars going on the road, you have motorcycles, you have autos, and you also have probably a bullock cart and things like that. And one way to incorporate that is now talk in terms of the average maximum velocity of everything on the road. So let us say the same road is being used by car that can go very fast, but also an auto that cannot go very fast, or an e-rickshaw that has a limit of the speed it can reach. Then many a times we need to consider the velocity of the slow moving objects or slow moving vehicles on the car, right? So one way to do that is to define some kind of an average maximum velocity of all the vehicles on the road. And finally, once we have defined this average, we can also define some kind of a traffic heterogeneity that depends on the deviation from the average from each of the type of vehicle, right? So if beta is bigger in this case, that means the traffic is more heterogeneous. If let's say all vehicles are having the same maximum velocity, then this beta is going to be 0, because the average velocity is same as the maximum velocity of each of the objects, right? So in that case the beta will go to 0. But if there are larger deviations of the maximum velocity with the average, the beta is going to go up, and we may have ways in order to account for the traffic density, traffic heterogeneity parameter beta as well, right? So one can keep on going and have more and more improved model rather than giving up in the very first step, right? If we start from a very simplistic model, which is slopiest possible model, but still encompassing the basic physics, that the model in that case, our case, was the case when we assume that there is no traffic and all the cars are going at a constant velocity, right? So with this idea, I want to now finally come to the question of like the condition of jam. And there is something that very interesting happens in the condition of jam. That is, once you are, let us say, approaching a railway crossing or somewhere, now all the vehicles are very close together, and now your speed is not dependent on how much fast you can drive, but it depends on what is the slowest vehicle on the road, right? Let us say, for example, if you are trying to cross the railway crossing along with a bullock cart, then the velocity or speed of the bullock cart determines the traffic speed rather than your speed. On the other extreme, if there is very less traffic, of course, you can go as per the speed limit of the road or the maximum speed of the car, whatever the case may be, right? So, in this case, for low traffic, the velocity of car will be the maximum velocity of the car or the speed limit. And in this case, the velocity of the car is the maximum velocity of the bullock cart, or maybe even lesser in the condition of a jam, right? So we can keep on improving this model further, but I hope I made a point regarding how to approach a modeling problem. So with that, I want to stop here, and we will do more examples in the following classes. Thank you so much.